Okay, so welcome to Thursday, day 4 of the CESM tutorial. This slide, like the days before, we have Meet a Scientist and another tour. So I've put the Meet a Scientist folks here. This is the last Meet a Scientist session. So if you did not meet with anyone and you want to, and you see some of these blank spaces, come talk to me as soon as you can, and hopefully we can add you. And then the tour folks are here. I want to reiterate that if you're doing the tour, you should eat lunch at 11:30 so you get a chance to eat. I also wanted to make a request for the Meet a Scientist that if you're working, well, actually we don't have a morning lab session, so this probably won't be an issue, but if you're gonna work over lunch, if you could go to the library so that they can kind of have their little group meetings. I think there's been some confusion, at least with the scientists, about people in the rooms, like, are they supposed to be talking to me or not? And anyway, I just want to point that out, and I'll put this up at the breaks as well in case you need to find your name and where you go. And I just want to point out again the code of conduct, especially the show appreciation for the helpers and each other. You know, all the people from NCAR are volunteering their time to help with this. They're all experts, so we want to just really acknowledge that they're here to help and to be patient when they're trying to make the rounds if we do get to a point where there's a lot of questions at once. All right, so first question, how are you bearing up? Cecile showed you her picture of a bear. This was earlier in June, not January. And I just figured I'd show you too. There are bears that come around. They don't come around very often, but this is our backyard. And I was like, why is my dog going nuts? And he just trailed this bear the whole fence line, barking at him. And fortunately, the bear was kind of like, nah, whatever. But this picture, you can see my dog like, oh my gosh. Less fortunately, but no pictures. The next morning, the bear came back, and they had a little standoff by that tree. So nobody got mauled, but it was very exhausting. And then because you couldn't really see my dog, I included the pictures of my 2 dogs here, because most people like cuddly animal pictures. It was this one that had the standoff with the bear. All right, one thing I just wanted to announce, a lot of you have been taking pictures during the talks. That's totally fine. I'm not telling you not to do that, but I do want to point out that we're being very efficient with getting the lectures up on the website basically the day they're given. So the CESM website is here. Actually, let me just go to this. The website's right here. If you click right here, the streaming from the different morning and afternoon sessions is up. You can see that some of them are like 2 hours long, so we haven't broken them up by lecture or anything like that, but if you wanted to rewatch anything, you can. And then, oops, hang on. I went too far. And then if you click up here where it says agenda, presentations, resources, you can go down, see the agenda. And now some of it's not quite updated. Gokhan didn't give this talk because he was stuck in an airport. I did, but you can still click on that and see the slides that I presented that day or any of the other days when we've already had presentations. So I wanted to point that out. And then today is more Ocean Day, and we're moving into more specialized lectures to some extent too. I wanted to point out with the specialized lectures, they're shorter in time. So the 2 specialized lectures takes up the same amount of time as a component lecture, but if you're kind of feeling like lectured out because it's more quantity of like number of lectures, if you need to just step out for a second or something like that to like clear your head, that's totally fine. So with that, today's agenda, the morning we're gonna have 2 component lecture talks about the ocean, and then we're gonna have 2 special lecture talks about model tuning and coupling and climate variability. So there aren't any morning lab sessions today. And then at lunch, there's the Meet a Scientist, the 3rd group. And I put it out here, if you wanted to work, go to the library instead of hanging out in like the Damon room. And the tour will meet just in this front lobby area at 12. And then in the afternoon, we have, again, 2 specialized lectures, paleoclimate and porting. So these specialized lectures, the purpose is that they're kind of associated with some of the working groups. So there's a climate variability and change working group. There's a paleoclimate working group. They're not giving component lectures because they kind of use the full model, but we wanted to give a chance for you to understand some of the things going on in those working groups. And then there's a software engineering working group, and also you just can't run the model without some software engineering. So understanding model tuning and porting is important for that. And then this afternoon, in the normal afternoon lab session, we're gonna have The lab exercises, we're going to put you guys in breakout rooms. I'll explain that closer to the actual lab exercise. And that's about diagnostics and tools for analyzing the model. And then if you get done with that early and you want to go back to any of the exercises, that's fine. Or if you want to run multiple components diagnostics, that's fine as well. All right, so without further ado, we will start the first presentation. I'm going to let you start this. Here's this for you. If you have a cell phone in a pocket, they say still don't put this in the cell phone pocket. Okay. All right, so our first lecture this morning is by Gustavo Marquez. He is in the ocean section. He's an oceanographer, and he is the primary model developer for CESM 3, which is using a different ocean model than CESM 2. So if you're interested in ocean modeling, and you might want to know what's going to change when the new model comes out in a year-ish, he's going to be really the expert for that. He also is interested in large-scale ocean circulation and ocean ice sheet interactions and things like that as well for his own research. So thank you, Gustavo.
Thank you, Alice. Good morning, everybody. Alice forgot to say that we're now getting to the most important part of the tutorial, the ocean component, as Peter liked to say. So I will give you the basics of ocean modeling, a general overview of the models that we are using with CSM. And then right after, Peter will go more into the advanced part on the parameterizations and physics. So you can save all your hard questions to Peter. He's in the business way longer than I have been. Also, if you like hiking, Peter has climbed all the 14ers in Colorado. So you can ask questions about that to him as well.
And he knows a lot about birds.
That's right. Okay, so just a general overview of what I'm going to talk about. Start with some general ocean modeling considerations, so the challenges for ocean modeling, some of the ocean properties, the governing equations, boundary conditions, and also the horizontal and vertical securitization. And then I will dive into more details on the Parallel Ocean Program version 2, or POP2. This is the ocean model that you guys are using for this tutorial. This might be the last time that we are giving the tutorial with POP. The next model that will be supported within CSM is the Modular Ocean Model version 6, or MOM6. That's the model that I primarily work with. CSM switched models a few years ago, although in terms of science, we're still using POP2. So we have MOM6 as an available component. It's an optional component, but it's not scientifically validated yet. So over the next year or so, that's when we will do the transition in terms of switching science applications to MOM6 as well. But I will give you some of the details of MOM6 and try to compare how, with respect to POP, how it varies. And then I'll end with some helpful resources. Okay, so the first order challenge in terms of ocean modeling from a numerical perspective is the land boundaries. So is the land, how the land controls the ocean motions. And I'll play this animation from the Perpetual Ocean that was done with the MIT GCM. Just pay attention how, what the features that you see, like how the land is controlling, for example, here in the Florida Strait, it's just the effect of the land, and there's the Earth's rotation as well. There's small islands that need to be represented, for example, the Bahamas here. Just get a sense of how the ocean currents are being shaped by the land boundaries. Now we're going to the equatorial region, the Atlantic, going all the way to the south tip of Africa. These are the so-called Agulhas currents. Look how they're shedding. They are formed in the Mozambique Channel, so between Madagascar and Africa. Again, look at the divergence that the Madagascar is helping generate. So just to make the point, that this doesn't happen in the atmosphere. We don't have the equivalent of the side boundaries. So that plays a huge role in the ocean circulation. Okay, there's also the spatial and temporal scales. So this plot shows on the y-axis, these are time scales. On the x-axis are spatial scales, going from millimeters to many thousands of kilometers. And then each bubble here represents a process. So going from very small and fast, like capillary waves. Where's my mouse? Oh, I don't see my mouse. On the left lower side, you see capillary waves, and on the right upper side, you see, for example, climate change. So with a 3-degree model, rather, so this is the coarser resolution that we support, these are the type of processes that we can represent. So we can represent climate change, a little bit of El Nino, seasonal cycle, barely some of the eddies and fronts, like very little. Then if we go with a 1-degree model, which is the model you guys will be running, then you move slightly to the left, meaning we can represent slightly smaller scales, although we don't run for as long, like we cannot do many 10,000 year simulations as we can do with the 3-degree, but now we can solve slightly better eddies and fronts, partially still needs to parameterize a lot of these. Now, if we go with the highest resolution that we have, which is the 1/10, we start to resolve a significant part of the eddies and fronts, some of coastal upwelling, but still there's a lot to be parameterized or represented in terms of the resolved flow, which is what Peter will go into details on the second part of the ocean lectures. Now, the bottom line is ocean models simulate climate. Like we can resolve well all the climate, very large scale processes. If you do an analogy with the atmosphere, now this is a workhorse 1-degree atmosphere, same type of plot. So we can resolve a lot of the tropical cyclones, for example, with that. So the bottom line is atmospheric models using climate simulations simulate the weather. So very, very different. So we need much higher resolution in the model in order to have the same effect, in quotes, that is simulated in the atmosphere of like eddies, mesoscale processes propagating and so on and so forth. Okay, so because we don't represent these spatial scales and also temporal scales very well, we need to parameterize them. So on the left, this is a simulation that was done with a 1/10 of a degree grid. So what we call that high resolution. Again, we are looking at the tip of Africa. So these are the Agulhas rings being represented. Now on the right is the same simulation done with a 1-degree, much coarser resolution model. So notice how you don't see all these eddies and waves. So we need to parameterize that. That's a big deal. We'll learn more about with Peter on the second lecture. So all these subgrid scale turbulence must be represented somehow. So why is the temporal scales much smaller in the ocean? And that goes back to the Rossby rays of deformation. So basically the density change from top to bottom are much smaller than in the atmosphere than in the ocean, which makes the Rossby rays of deformation much smaller in the ocean. So in the ocean is hundreds to tens of kilometers, while in the atmosphere is like thousands of kilometers. And the radius of deformation is basically the vertical stratification times the depth of the ocean. This is the first baroclinic radius of deformation divided by the Coriolis parameter F. So this is a kind of a map, global map of the Rossby radius of deformation. Just give you an idea, like near the equator, and how this is divided. Like this is the resolution required to resolve the first baroclinic Rossby radius of deformation. So near the equator, it's purple-ish blue, so order like 1/2 degree you can resolve. So it's the Rossby deformation is 200-ish kilometers. So if you have a model that's less than 100 kilometers, you can start to resolve that. So 1/2 degree you can resolve. Then if you go mid-latitudes, you need something like a 1/16, 1/8 of degree to resolve. And then high latitudes, more of a 1/12, 1/16. Sorry, before I said 1/16 is 1. So mid-latitudes 1/6, high latitudes 1/16. Now, also notice shallow regions, you tend to have a very small radius of deformation, therefore you need a very high resolution. So if you look at the coastal regions, it's red, so you need a very high resolution. Even the highest resolution models that we have don't resolve the mesoscale field in these locations. Another challenge is the way things mix in the ocean versus diabatic, so exerting work, and adiabatic, so without exerting work. So this is a schematic of a conceptual model for eddy fluxes in the upper ocean. The gray lines represent isopycnal, so lines of constant density. Then the blue arrows are the direction of where mixing occurs. So there is a transition between near the surface and at depth. So near the surface, the mixing is mostly horizontal, mesoscale mixing, I should say. There's also the red arrows, which represent the vertical mixing. So near the surface, vertical mixing is very strong. Horizontal mixing, it happens actually parallel to the boundary, so actually horizontal. Then there's a transition layer. Then in the interior, the mixing done by the eddies is along isopycnal. So that's why the blue lines the blue arrows don't cross the gray lines. And then you have very, very little cross isopycnal mixing. And representing that in the ocean models is challenging. If by definition we use the truncation version of the equation, so you with the advection schemes, you have the truncation errors. When we represent that numerically, then a lot of our businesses try to minimize that spurious or numerical mixing, because a little bit will cause a lot of unintended changes in water properties. So a lot of the business that we do is try to minimize numerical mixing, especially in the interior. And the consequence of having very little mixing once the water is in the interior is that we can track the water masses. We can name and track them. So this is a plot showing different water masses. You have AABW, which is the Antarctica bottom water, formed, as the name says, around Antarctica. You have the North Atlantic deep water, and so on and so forth. So that is a consequence of the relatively weak mixing in the interior. Once the water masses are formed, they tend to preserve their temperature and salinity. So this is what I just said. So in terms of what that means is in terms of equilibration timescales, it takes a really long time to adjust the ocean, especially the deep ocean. And we can estimate that just using scaling arguments. So using h squared, h is the depth of the water column, divided by the vertical diffusivity, for example. This gives us an estimate of how long it takes for the ocean to adjust at, like I'm talking about the whole ocean, like at depth as well. And this number is on the order of 20,000 years. So that, imagine if you run an ocean model and you want it to have like an adjusted state, this is how long you need to run for, like, if you're interested at processes that happen at depth. For analogy, if you look at the dynamical adjustment timescale, so we can use the phase speed of the non-dispersive long Rossby waves to do that, which is given by that equation. It takes approximately 2 years for the waves to cross the Pacific Ocean. So it's much faster, the dynamical timescale compared to the mixing timescale for equilibration. So the bottom line for climate studies is that performing long climate scale multi-century simulations at eddy permitting or eddy resolving resolution, it's not practical. You can do a few, but not like for climate, we need to do many, and that's not practical, still with computers nowadays. Spurious mixing in the interior can significantly degrade the solution, so that's the business of numerical errors. We must live with the deep ocean not being at equilibrium in most simulations. I didn't mention this, but it's also, most of you probably already know, that the heat capacity in the ocean is much larger than the atmosphere. And because of that, we should say, Peter likes to say, I pray to the ocean every day, because the ocean has been taking up a lot of the heat that as a consequence of increasing CO2. So it is a consequence of the larger heat capacity in the ocean that makes the ocean an important heat reservoir. And also the ocean contains the memory of the climate system and has important implications for decadal prediction studies. Okay, so now moving on to the equations solved by the ocean models. We have 7 equations, 7 unknowns, 3 velocity components, U, V, W, potential temperature, density, pressure, salinity, plus if you're doing BGC studies, there is 1 equation for each additional tracer. It doesn't have to be BGC studies. Sometimes we use CFCs even without BGC. So if you have CFCs, you have an extra equation for the CFCs. We also have 6 approximations, starting with the hydrostatic. So the hydrostatic approximation, basically we ignore all the vertical accelerations that are smaller than gravity. And when the ocean becomes statically unstable, the vertical overturning normally occurs. So for example, if you have a dense water flowing down the slope, there's overturning, so Kelvin-Helmholtz instabilities, that's in the real ocean. But because we use the hydrostatic approximations in our models, we don't represent those Kelvin-Helmholtz instabilities. Or for example, like just deep convection is another example. So the mixing accomplished by that has to be parametrized. And again, there will be a follow-up lecture to talk about the parameterization. So, but we use, I think, all the ocean models that are part of climate models perform the hydrostatic approximation. We also have the Boussinesq approximation, where the density can be approximated by a mean value plus a perturbation, and the perturbation rho prime is much smaller than the mean value rho naught. Therefore, we can assume that the density is constant in most of the equations, with except of the hydrostatic equation. Also have the continuity or incompressible flow. We cannot deform the seawater, so what flows into a control volume must flow out of that control volume. So the volume within that cube must be constant. The thin shell approximation. So basically, this is like if we were to use an aspect ratio to quantify the ocean, the best approximation is a sheet of paper. Like that's how the vertical scale compares with the horizontal scale. And because of that, and in conjunction with the fact that the horizontal motions are much larger than the vertical motions, this is called the traditional approximation. That and the thin shell approximation means that within the Coriolis force, we can retain only the horizontal components due to the horizontal motion. So when you work out the Coriolis component in the Navier-Stokes equations, there's the cosine terms. These can be neglected because of the thin shell and the traditional approximation. So that simplifies the equation. And number 5, this is the spherical Earth. So geopotential surfaces are assumed to be spheres. For the purpose of this talk, I'm going to show you the equations of motions in Cartesian form, but no, in the model we have them in spherical coordinates. And then we have the turbulent closures. So this is kind of it's listed as approximation for the ocean modeling within climate simulations, because we rely a lot on the parameterizations that Peter will talk about. Okay, so that leads us to the Boussinesq hydrostatic equations in high coordinates. Again, I'm going to show you in Cartesian form. So the first one is the horizontal momentum equation. This is in vector form, so there's U and V here. Then in the vertical, because of the hydrostatic approximation, it reduces between a balance between the pressure gradient and gravity. So this is the hydrostatic equation. Then we have the mass conservation / continuity equation, which with the Boussinesq approximation is simplified by equation 3b. Then for each tracer, we have an equation. So this is for potential temperature. So it's rate of change. Potential temperature is balanced by advection and diffusion. I'm not including source and sinks here, but no, in the ocean, we also have source and sinks. Similar for the salinity transport, and all other tracers that you have is the same equation. Then we have an equation of state that closes the, now we have 7 equations, 7 unknowns, and we can solve that. In terms of boundary conditions, we have flux exchanges at the surface, so momentums and tracer is, there's a source and sink sometimes at the surface. In POP, there is no freshwater flux. Instead, we use the so-called virtual salt flux, so it's like is equivalent to what rain and evaporation would do, but we don't actually evaporate and put water in the ocean. You do via virtual salt flux. That's not the case in MOM. It has some implications. I'll talk a little bit about that in the next slides. At the ocean bottom, we have no tracer fluxes, although in MOM, there is an option to enable geothermal heating. There's the normal velocity at the bottom is 0, and we use a quadratic bottom drag. So this is a bottom condition in the viscosity term of the momentum equations. Then in the lateral boundaries, we have no tracer fluxes. The flow normal to the solid boundary is 0, and we use the no-slip boundary conditions. Okay, now moving to the horizontal grid. For POP, we use the so-called Arakawa big grid. So the Arakawa big grid, you define tracers at the cell center, so that capital T, this is where tracers are defined within a grid cell. And then the corners of the grid cells is where the velocities U and V reside. So this is a top view of the grid. And the advantage of the Arakawa big grid is that it naturally fits the no-slip boundary conditions. You have a better representation of the Rossby waves at coarser resolution relative to the Arakawa C grid, which is the one I will show next. And you also have small altercation errors in the computation of the Coriolis terms. The disadvantage is that you cannot represent a single point channel. So the plot on the lower right shows a schematic top view of a grid using the Arakawa big grid. And in green, you have the land points, and in blue are the ocean points. And in order to have a channel, you need to have at least 2 grid points between the land points. Otherwise, the flow is not going to go through, and that's because the velocities are at the corner of the grid. So this is the grid used with POP2. Also, another disadvantage is there's larger truncation errors in the pressure gradient terms with this Arakawa B grid. Now, this is the Arakawa C grid. Again, tracers are in the middle of the cell, capital T. Then the V velocity is at the same I point that the tracer, but upper in the J, so at the interface, top and bottom interface, but at the same J point. So you can see, unfortunately, I have the miles, but just at the top and bottom, you have a V point. So that's where the V velocity is. Similarly, the U point is at the same J point as the tracer, but different I indices, so -1 and 1. So the lateral interfaces in the middle. And the advantages of this type of grid, it allows for a single point channel. So now if you have a single cell between 2 land cells, the flow can go through. And the disadvantage is that the Coriolis acceleration terms require horizontal averaging, because now you don't have the velocity terms on the same point, and making the initial gravity waves, which is related to the Coriolis force, less accurate when you use this type of grid, and also is a less accurate dispersion relation for Rossby waves at coarse resolution compared to the big grid. So for really coarse resolution, like 3-degree ocean models, the B grid offers a lot more advantages in terms of reducing the errors compared to the C grid. So again, the C grid is what we use in MOM6. There's also the choice of vertical coordinate system in the ocean model. So we talked about horizontal discretization, now moving to the vertical discretization. And the vertical discretization is one of the most important in conjunction with the horizontal aspects of the model design. And there's basically three main coordinate systems that have been in use. The so-called Z coordinates. So this is the one on the far left, where you have the distance between the cell thickness is constant throughout the whole ocean at a certain vertical index. It's a function of height. So this is what's used in POP. The advantage is it's simple to code, like because it doesn't, the surface doesn't vary with space. So coding ocean models in Z coordinates tends to be simpler. Then the one in the middle is the so-called sigma coordinates, or terrain following sometimes. It's used a lot in regional applications. So that in that case, your coordinate system is following the topography, as you can see in the bottom. Not very used for climate applications. And then the one on the far right is the so-called isopycnal coordinates. Now each interface represents a density value. And the difference between two interfaces, the average between two interfaces is the value, the density value of the cell center. So waters that rely between two interfaces must have the density represented by that layer. So in that case, your coordinate is adjusting to your water mass. It has a lot of advantages in terms of minimizing spurious mixing, for example. It is much harder to code ocean models that are in isopycnal coordinates. Now you have your vertical coordinate is changing with time, so your thicknesses are changing with time, so it adds another complexity to the system. So each one has advantages and disadvantages, as I mentioned, and in a way to try to combine them, people have developed these so-called hybrid coordinate systems, where it's a combination of one or multiple of those systems. And this is an area of very active research and development in numerical ocean models. So the vertical grids used in CSM, starting with the ones on the left, so these are the ones used in MOM6. We support two coordinate systems at the moment, a Z star, so no Z height dependent coordinate, which has 65 levels, then a hybrid between Z star near the bottom and isopycnal at depth. So that's the one on the bottom left here. So if you look near the top of the plot, it's kind of shaded. That's a lot of interfaces. So this is where Z star, and then below that, it switches to a density based. And then the ones used with POP we only have the Z coordinate, and it has a 60 level. The shape of when we use Z coordinates, we tend to always have the same shape. So this is kind of this hyperbolic tangent. You have, oh, my mouse is back. We have a lot of vertical resolution near the surface, and then exponentially increase as you go to depth. At depth, it tends to be much coarser. And this is the same that's done with the Z star in MOM6. Although we have different levels. We have 65 in MOM, 60 in POP, and then for the hybrid in MOM, we have 75. Okay, now, what are the options that we have for forcing ocean models within CSM? So basically, you've already learned about CompSet. We run 3 CompSets in 99% of the time in the ocean model. So first one is the fully coupled mode, or so-called big CompSet. A lot of you will be running that, or all of you, hopefully. Then we have the forced ocean, so that's the so-called C CompSet. So with the C CompSet, all the other components are represented by a data stream. And then we have the ocean sea ice coupled, which is the so-called G CompSet. So most of the time you're developing the model, we use the G CompSet, which is forced atmosphere, ocean, and sea ice evolving prognostically. And within the forced atmosphere options, we have basically three options. We have the core forcing interannual option. So that's the one on the top. Then we have the normal year forcing. This is repeating the same year over and over. And then the interannual forcing goes from 1948 to 2009. And these are the papers describing these two forcing protocols. And then we have a newer one, which is the GRA 55 do, which goes from 1958 to 2018. So this is also interannual, it's changing every year. Okay, so now diving a little bit into the POP dynamical core. So as I mentioned before, POP is a level or z-coordinate model. It was primarily developed at Los Alamos many years ago. It resolves the two-dimensional primitive equations in general orthogonal coordinates in the horizontal with the Boussinesq and hydrostatic approximations. We've learned about those. It has a linearized implicit surface formulation that's used for the barotropic equation for the surface pressure or surface height. The global integral of the ocean volume remains constant because of the freshwater fluxes are treated as a virtual salt flux. So that's what I mentioned before, like we don't actually dump water in the ocean. We represent the effect of precipitation and evaporation via virtual salt flux with a constant reference salinity. And what that means is if the volume goes up in one location, it must go down somewhere else to compensate for that. This is, we have a few grids supported within POP. So the first one is the so-called displaced pole. So if you look, God, lost my mouse again. If you look on top of Greenland, there is a white point. So that's where the pole is in this type of grid. So that's what we call displaced pole. Is not the actual North Pole, but rather on top of Greenland. And this is what's used for GX1. So that's the 1 degree simulation grid that you'll be using, and also the 3 degree grid that's used for paleo and testing. And that grid also has an equatorial refinement that will go much higher resolution near the equator. And we also have the tripole grid. So the tripole grid, as the name says, has 3 poles. There's 2 in the Northern Hemisphere, 1 in Russia, 1 in the Canadian, and then the one in the Southern Ocean. So that's what we use for the high resolution 1/10 of degree in POP. The tripolar grid is also what we used in MOM. I'm going to show you the MOM grid in a second. So this grid, the 1/10, is eddy resolving almost everywhere. We saw that map of the global ranges of deformation, and you can go back and have an idea where this grid is not resolving mesoscale. And if you want to learn more about the ocean model grids or grids in general, there's a reference here by Murray, 1996, that gives a lot of details on the types of grids. Okay, now jumping to the MOM6. So MOM6 is a finite volume solver. It has the hydrostatic Boussinesq approximation, but it also has the option to do non-Boussinesq, solve the non-Boussinesq equations. And that is very appealing for sea level studies, although we haven't exercised the non-Boussinesq option within NCAR yet. In addition to that, MOM6 also uses the so-called arbitrary and Lagrangian Eulerian framework. So this allows the model to represent a combination of vertical coordinates. So it's kind of a generalization of the vertical coordinate. So we tend to refer that as the ALE algorithm, ALE. And because of that, there is no vertical CFL limit. So there's no vertical velocity in the model. The vertical velocity is represented by the grid going up and down with the motion. So the grid is adjusting with the flow. So that means we can go ultra fine resolution in the vertical without having to change the time step. The model subcycle the gravity waves, and there's also built-in wet and drying, and I'll show you in the next slide how that comes into hand. So the plot on the right shows the different vertical coordinate systems that we can use within MOM6. So you can use sigma, z, or density row as a pick node, or a combination of any of those. Or you can create your own coordinate systems and implement, because the AO algorithm allows for that type of flexibility. So the MOM6 is primarily developed at the Geophysical Fluid Dynamics Laboratory from NOAA, and we have a lot of support from them. There's also many other groups that are currently using MOM6, in addition to NCARS. There's NOAA, EMC, universities, NASA, and the US Navy is also starting to use MOM6 as well. And we have these bi-weekly meetings where we all get together to discuss development strategies. It's an open development model, so that means anyone can contribute. You can go, if you download the model and you find a bug, or you have studies a way to improve the model, you can go implement. We are open to anyone in terms of receiving contributions. The community is growing, as I mentioned before, labs and universities. And the way we all work is we have a centralized fork, which is the one in red we call the main branch. And it sits on a particular fork, and then all the entities communicate with that. And that's how we can go back and forth and all contribute while keep syncing the model with each other. I'm not going to go into details, but no, there's a lot of parameterizations available in MOM6 in terms of mesoscale eddies, surface boundary layer, sub-mesoscale eddies, shear mixing, shortwave penetration, so on and so forth. So it's way more complete in terms of options than POP. The analogy is like you have maybe like a Volkswagen Beetle is POP, and then like maybe, I don't know, Ferrari, like, yeah, Ferrari would be like MOM6, like way more complex to deal with. Or maybe, is a Tesla complex? No, Tesla's not. Anyway, yeah, the Beetle and Ferrari, I think is better. The wet and drying capability I mentioned before comes into hand when you want to do, for example, interaction between ocean and ice shelves. So this is a simulation where there is an ice shelf here on the left in white, and then the ocean will start melting that ice shelf. The bottom here represents the bedrock. So because it's built in with this wet and dry, that means all these points below the ice sheet are actually ocean with a zero thickness. And as the ice sheets start melting, they become having a fine thickness, and it just works well. And another example is like in a beach, like the movement of the water back and forth within the beach. That's simpler to do with MOM, although we don't represent like that small of a scale in the climate model. But anyway, it's built in with MOM6, and that it brings a lot of capabilities, opens a lot of possibilities because of that. So you can see now I highlighted the initial ice shelf front. You can see how the ocean was able to handle a point that was ice and now became ocean relatively easy. Starting in CSM 2.2, so this was a few years ago, there was a functional release of MOM6. The code that you're using has MOM6 as an optional component, and it's being developed very rapidly, and it has not been scientifically validated, as I said before, so be careful, use at your own risk. I'm happy to help if anybody's interested in running MOM, just please come to me and we can work together. And these are just instructions if you want just to try on your own. It's the same procedure you've been doing with POP, like case setup, case build, case submit. You can do with MOM, and these simple instructions, you can use the latest CSM tag to do that. I'm not going to go into details, but I'll leave it here for you if you want to go later on your own. And again, please feel free to reach out to me if you have any questions. There's also detailed instructions on GitHub. These are the available configurations. So we go, as I said before, there's C comp set, G comp set, and then B fully coupled. And we have 3 different grades within MOM6 at the moment. We have the workhorse, which is a 2/3. It's not a 1 degree, it's a 2/3. Don't ask me why. Workhorse, and then we have the 1/4 degree eddy permitting that we use for research and testing. And then we have a 1 degree, which is the same grid as used in POP, which is only used for testing. This is the MOM grid, tripolar grid, nominal 2/3 of degree with refinement in the equator. Again, the 2 poles are in Russia and Canada. And currently, we've been doing century-long simulations with CSM MOM6, and they produce a stable climate with bias and drifts that are less or equal than what we get with POP. So just to give you an idea, the top plot is the sea surface temperature average over many years with MOM in fully coupled. The middle is observations from World Ocean Atlas, and the bottom is model minus observations. So the bias that you see on the bottom is similar to the bias that we get with POP. And we're actively working to improve that. We also have the similar type of issues that we get in POP, but I'm not going to go into details here. We have alternative configurations that can be done with MOM6, for example, aquaplanet or the ridge planet. So the one that's playing now is an aquaplanet. There's 2 caps at the north and south pole, just because we need some land points to put the singularities in the grid. And we also have the so-called ridge. So now it's this kind of same thing, but we have a ridge crossing the ocean meridionally. So this was a work done by our grad student, Xiaoning Wu. She graduated. She is no longer doing research. But anyway, just to make the point, we can support additional configurations. We also have the high resolution MOM6 at 1/10 of the grid. So it's the same grid using POP. We are creating a 112 and a 136, yes, 1 divided by 36, which will be an ultra high resolution coming up soon, hopefully. We have the ability to do regional configurations. So the plot on the left is the Eastern Tropical Pacific domain that's led by my colleague Scott Bachman. The one on the right is the Caribbean Sea and Gulf of Mexico, which is led by an ASP grad student from CU, Giovanni Seijo. So those are capabilities that were not present with POP, not doing regional simulations, and we are now able to do that. So this opens a lot of possibilities in terms of actionable science application. For example, in the case of the East-Tropical Pacific, is for coral reef management. In the case of the Caribbean, is for managing marine protected areas, etc. Okay, so now to the helpful resources. For POP, there's this web page that has a lot of information. So the POP user guide also has the BGC Marble documentation, the reference manual for POP, port validation, post-processing, so on and so forth. Again, this might be the last time we are teaching that. There's also the forum if you have questions for POP. This is the best way to get help. Once you guys go and do your research is through the forum. In terms of MOM6, we have the web page for CSM MOM6. There is also a series of MOM6 tutorials online. We are expanding the documentation via Read the Docs. There's also documentation for post-processing analysis. And again, there's a MOM6 forum within the CSM web server or within the CSM forum server. And this is the best way to get help. These are the references, and I'm happy to take any questions. Thank you.
All right. Thank you so much, Gustavo. So, okay, we got some questions. Yeah, I see you back there. Hang on.
Thank you, Gustavo, for that very interesting talk. I was wondering how the ocean model receives input from river runoff. Initially, I was thinking it might be more appropriate to do a regional model, but then seeing that MOM6 does a regional configuration, I was wondering if you could also touch on that.
Yeah. So I'll just jump on MOM because POP doesn't do regional configuration. So we spread the river runoff over a specified region. We tend to use like an area like is a half a circumference from the point of the river with a radius of 300 kilometers or so, and then we decay the runoff using some exponential function like 200 kilometers or so. So we do this spreading over a large region, and we put it at the surface only. we are working on doing the estuary box model parameterization in MOM, which means we will also mix in the vertical. So instead of putting everything in the surface as we're doing right now, the idea is to spread that vertically as well. Yeah.
Sorry, so I have two questions. The first one is a little more specific. Say, if I want to model the climate of the Southwest desert, so these are regional, right? The U.S. Do I have to, I want to see how sea surface temperature affect that. Can I use sea surface temperature from, say, the Gulf of Mexico and the Gulf of California, or do I have to use a global sea surface temperature input? And then, since we're saying, right, that for, I guess, larger time scale, we can't really resolve the eddies around the coast, does that affect how accurate my model will be in terms of the output?
Sorry, are you talking about global or regional?
Regional.
Okay, so in regional, everything I said about the challenge of climate modeling don't apply to regional because we can go much smaller domain and much higher resolution in the regional. However, we don't do fully couple in regional. It's only forced, right? So the ocean is, you're receiving the boundary conditions, including the atmospheric forcing, via data. So you cannot do climate studies unless you run a global model for the future, save the boundary conditions and surface forcing, and use that to drive the regional model. But it's a one-way response. But we can talk more later. Yeah.
Okay, thank you very much for this great presentation. My question mainly related to the approximations. What are the main rules that you choose the approximations, and how these approximations could affect the prediction of the ocean model?
Yeah, so the main rules is we use scaling argument in the approximation. So typical length scale, horizontal length scale, vertical length scale, velocity scales, and so on and so forth. That's how we can come up with all the approximations I listed. So you have the equations, you use scaling argument, and you say this term is much smaller than that term, therefore we can neglect. And these approximations work really well for large scale global ocean modeling.
So has the options to choose the different approximations than the one you used in the model? Or?
Yeah, there are options. One is, for example, Boussinesq versus non-Boussinesq, and that comes into, it becomes relevant for sea level applications, where in the Boussinesq, you assume that the density almost in all equations, but the hydrostatic is constant. So you always have a same density being used throughout the equations. In the no-Boussinesq, the density is varying in all the equations. So in terms of sea level rise, that gives you more accurate representation. But there are ways to correct, even when you use a Boussinesq approximation as well for that.
All right, we're going to do one more question. I know there are more, but I want to be respectful of the break too. So we'll do this final question, and if you have other questions, talk to Gustavo after. And I think you're coming to both the lab sessions today and tomorrow, so you might be able to ask him other questions during those periods. All right, last one.
I was really struck by the 20,000-year spin-up period to get it to come to equilibrium in an 1850 state. But of course, we also know that it wasn't in equilibrium at 1850, given the last 20,000 years. And I was wondering how you all deal with that challenge.
Yeah, that's a big challenge. Yeah, it's not that we had a constant forcing and then let the model, nature doesn't force and then stop and let adjust. Yeah, good point. It's constantly changing, which is even more challenging. The way we deal, so we need this spin up, especially for the tracers. So there are techniques that can be used to spin up the tracers within the model. You haven't met King Lindsay yet. He's a colleague of mine in the ocean section. He does a lot of the BGC development and studies, and he works with this Newton-Krylov solver. So it's a way to spin up the tracers and try to get I'm going to start using quasi-equilibrium state so we can perform the simulation. So there's techniques that are used that doesn't require you to actually run the model to get those quasi-equilibrium states.
All right. Well, thank you, Gustavo. As I said, if you have other questions, I know I saw a lot more hands, and I'm not trying to ignore you. I just want people to get a chance to have a break too. So Gustavo's available, and we'll see you back here at 9:30 for Peter's talk about the ocean. Okay. The first thing before I introduce the next speaker, I've noticed there are two really sad chocolate lollipops that are the only ones left. These were the main ones left. So if you want some of these sad chocolate lollipops, I had to move them so they can put the snacks out at the next break. I'll have them here and you can come get a chocolate lollipop. Okay. So our next speaker is Peter Gent. He's a senior scientist in the ocean section, though he's officially retired now. He has spent his career working on developing ocean models and has done a lot with parameterizing mesoscale eddies in ocean models. So the Gent-McWilliams parameterization, Gent is part of that name, is used in, I think, pretty much all global climate models, the ocean component of global climate models that I am aware of. He also has done a ton of service with CESM. He was the CCSM before it became CESM. Chief scientist. He's been on the scientific steering committee. He's won the CESM Distinguished Achievement Award. He got the Sverdrup Gold Medal. And besides that, he also is really interested in birds and hiking and squash and cricket. So without further ado, we'll start this presentation. All right, I think
use sunscreen and a hat, otherwise you'll end up getting skin cancers removed, as I did yesterday for the nth time, where n is quite a large number. So, as Gustavo said, here we are, Thursday morning. You're finally learning about the most important climate component, the ocean. The ocean has a large heat capacity compared to the atmosphere. So can anybody tell me what percentage of the extra heat has been put into the climate system since we started increasing CO2 in the Industrial Revolution? What percentage has gone into the ocean? Oh, you guys are too good. So the best estimate we have is actually 93%. And it's certainly over 90%. So all that heat that's coming in, 93% has gone into the ocean. Now, the extra CO2 that we've put out, what percentage of that has gone into the ocean to make it more acidic? Yeah, it's in sort of round numbers. About half the CO2 remains in the atmosphere. A quarter goes into the land, produce more leaves and greenery, and about a quarter of it goes into the ocean. So the ocean has taken up 90+% of the heat, a quarter of the CO2. So as Gustavo said, every morning when you get out of bed, you put your hands together and say a little prayer to thank the ocean. Otherwise, the climate would be so much worse than it is today. So, I'm going to talk about just two of the parameterizations, the vertical mixing scheme and the lateral mixing scheme about mesoscale eddies. Now, one big difference between the ocean and the atmosphere is that the ocean is forced from above. In the atmosphere, you get a lot of stuff happening at the surface, so you're forcing things at the bottom of the atmosphere. In the ocean, everything happens from above. So momentum, heat, and fresh water are all mixed down from the surface. So one of the most important processes in the ocean is that in the upper ocean, there's very, very strong mixing to get these things down into the ocean. And then once you get into the deeper ocean, there's very small, much smaller vertical mixing. So you need a scheme that can do this. And the one that's used is called the K-profile parameterization, which was first put forward by our colleagues in the oceanography section in 1994. So unresolved turbulent vertical mixing due to small-scale overturning motion is parameterized as vertical diffusion. And this was guided by a study of observations in the atmospheric boundary layer. So in the equation for the time rate of change of a tracer, you have d by dz of the vertical turbulence, and you parameterize that turbulence as minus a coefficient times the vertical gradient of the quantity. So that in the end, that equation of d by dt looks like vertical diffusion, d by dz of a kappa, d by dz of x. And kappa x represents the eddy diffusivity or eddy viscosity. Now, one of the things that characterized KPP compared to anything else that had been proposed before for the ocean was that it's not just a vertical diffusion scheme because the scalars have a non-local or counter-gradient terms. Now, old-fashioned me, I'm not going to lose my mouse. I've got a pointer, which as long as I don't drop it, I don't lose it. So, KPP involves 3 high-level steps. Determination of the boundary layer depth, D, the calculation of the small interior diffusivities, nu of x, and then evaluation of the boundary layer diffusivities, big kappa x. So these are going to be small, these are going to be large. And the diffusivity throughout the boundary layer depends on the surface forcing. As I said before, everything in the ocean gets mixed down from the surface forcing. It depends on the boundary layer depth and the interior diffusivity. And one of the things that KPP did, mostly because of these counter-gradient terms, as opposed to schemes which had been used before, was it produces quite large diffusivities below the boundary layer, which mixes temperature and salinity quite deep in times of very strong surface wind stress, such as strong mid-latitude storms. So, just to get in a little more quantitative, how is the boundary layer depth calculated? In stability, we always talk about the Bulk-Richardson number. And what you do is you go down in the ocean until you come to a Bulk-Richardson number, which has a value of 0.3. The Bulk-Richardson number is the difference between the surface buoyancy and the buoyancy at a depth d times the depth divided by the square of the velocity difference between the surface and depth d. So this is a sort of equivalent of a classical result in stability of shear flows, which says the Richardson number criterion should be a quarter to get stability. This time we don't use quite a quarter, but we use the value 0.3. So as I said, what you do is you go down in the ocean, looking at the depths until you come to a depth where this value is less than the criterion 0.3. And that's how the boundary layer depth, where the vertical mixing is extremely strong, is calculated. Now, these days we only have half an hour for these talks, so I'm not going to talk about that one. I'm going to instead show the example in the large et al. Paper of a comparison between observations at Ocean Station Papa, which is in the North Pacific. These observations were taken in 61, so some time ago. And it shows the distribution of temperatures throughout the year, March through February, at Ocean Station P. So what happens is these temperatures, these are degrees Celsius, you can't read them very well, but they go from like 5 to about 14. And as the ocean starts to warm up during June and July, always takes longer for the ocean to warm up than the atmosphere because of the heat capacity. You get warmer and warmer, so you produce a boundary layer depth which is small. Then, as in the fall, it starts to get cold, and there's more mixing from storms. The boundary layer depth gets deeper and deeper and deeper, so things are mixed down much farther. Over the winter, the boundary depth is as large as it gets, about 100 meters. And then during the spring, it decreases again. So the boundary layer depth in all parts of the ocean is smallest during the summer, deepest during the winter. And so the winter is the time with strong forcing, strong winds, where things get mixed down into the ocean. So the heat that's gone into the ocean gets in at the surface, but then it gets buried by a deep boundary layer in the winter, and then the next summer, that's below the boundary layer. So that's how you get heat, momentum, and other things below and down into the ocean. Now, this was the simulation done by KPP, and in the paper they claim this is a really good simulation, but you can make your own mind up about that. But they claim that this was much better than any other scheme that had been used so far. And it's, it's not bad. I mean, it gets the boundary layer depth right, goes from about 25 to about 100, gets deeper and deeper during the fall and then in the winter, and then. So that is all I'm going to say about the boundary layer scheme, because I want to get on to my favorite parameterization. So we first proposed this in 1990, but nobody, including myself, thought it was going to be any good or make any difference. So it took actually a long time before anybody started really taking it seriously. I advise you not to read that paper. If you want to learn about the Jet McWilliams, there's a much, much easier paper to read called 2020 Hindsight, which was produced after 20 years of this parameterization in ocean modeling in 2011. That's the one to read. So Gustavo did a nice job stealing some of my things here. This is a GFDL model at 1/10 eddy resolving. This is the sea surface temperature, tropical Pacific. You've got tropical instability waves, and you've got all sorts of variability down to small scales in the ocean. Scales, including the greatest eddy energy in the ocean, is at the eddy scale, which is about 100 kilometers and less. And that's what we don't resolve in climate models of the ocean. And that's what needs to be parameterized. Now, not only did he steal some of my best jokes, but he stole one of my best slides, because you've seen this already. So this is the difference between what you get for the Agulhas retroreflection off Southern Africa in a 1/10 degree model and in a 1 degree model. And as you can see, there's a lot more variability in the 1/10, which resolves eddies, compared to a 1 degree that doesn't. And he even explained extremely well why the baroclinic deformation radius is much smaller in the ocean than in the atmosphere, because the vertical temperature gradient, vertical density gradient is so much smaller in the ocean than in the atmosphere. The only place where it gets anywhere close to like 100, 150 kilometers is in the tropics. And that's because the water, surface water, is so much warmer in the tropics, so you get a bigger density gradient compared to the deep. In the high latitudes, the surface water is cold, so you get a much weaker vertical density gradient. And that's why, as you get towards high latitudes, the deformation radius is actually on the order of 10 kilometers. So even at eddy resolving with 10 kilometers, you're not really resolving the eddies. So even if you use a 1/10 degree, you still have to do something about the quite large variability that's smaller than that. So why was GM needed? So in very early ocean models, the effects of unresolved eddies were parameterized by a Laplacian horizontal diffusion with a large value on the order of 1,000 meters per squared. So the diffusion was along depth surfaces, and that was easy because those are all z-coordinate models. So the diffusion was along the coordinate system. But we know from ocean observations that mixing along the constant density surfaces, along isopycnals, is on the order of 10 to the 7th times the amount of mixing that's across isopycnals. And again, as Gustavo said, the reason for that is that you can name ocean water masses, that once they're formed, once they're buried, you can name them, like Mediterranean water, which is very saline. That, once it gets down in the Atlantic, that salinity doesn't diffuse across density surfaces very quickly at all. So you can follow Mediterranean water as it goes down and down and down and goes west in the Atlantic. And that's why all the oceanographers, the old guys who worked at Woods Hole and Scripps and whatever, always named these water masses because the diffusion across isopycnal surfaces is so small once you get into the deep ocean. Now, if you've got a coefficient of mixing along depth that's order 10 to the 7 times what should be going across, if the angle here is greater than 10 to the minus 7, then you're producing spurious diapycnal mixing compared to what should be happening just because the diffusion is along horizontal surfaces. This was first diagnosed by George Veronis, and I see that it's nearly 50 years since he did this. And what he showed was this spurious upwelling in the western boundary currents. It produced spurious upwelling in the western boundary currents, which short circuits the North Atlantic meridional overturning circulation. And I'll show this a bit more in detail later. So it was then recognized by the 80s that the mixing, even in z-coordinate models, needed to be along the isopycnal surfaces and not across them. So this was first introduced by GFDL in the early 80s. So that's represented by, this is a temperature equation, that's represented by this diffusion being along isopycnal surfaces. What was proposed in 1990 was that in addition, the eddies, as well as diffusion along isopycnal surfaces, had an extra advection over the temperature and salinity. And this was proposed that it's a three-dimensional velocity, zero divergence, as usual. And this was the form that was proposed, where this velocity had proportional to the gradient of a undisclosed, again, coefficient times the horizontal density gradient divided by the vertical density gradient. And this was proposed in that 1990 paper that the eddy-induced velocity in addition to diffusion along isopycnal surfaces. So when I start talking about this, I get all choked up, so I've got to... So again, in the impacts of time, I'm going to do it. Now, the area of the ocean where GM has the greatest influence is in the Southern Ocean. In the Southern Ocean, there's a thing called the Antarctic Circumpolar Current, and it goes round Antarctica, so it's named pretty well. And it's the only current in the ocean which goes round the globe. All the others are in not closed basin, but in basins, the Gulf Stream, Kuroshio are there. So it's the only one that goes round the globe, and that makes it more like the atmosphere, the jet stream, and it produces different dynamics. So you've got an Antarctic. This is Antarctica. These, for instance, are all these water masses named, which Antarctic bottom water, North Atlantic deep water, Antarctic intermediate water. You know, and the oceanographers still like to name their things. This Antarctic circumpolar current is going from west to east, so it's coming out of the board at you. And it's forced by a zonal atmospheric jet in the southern hemisphere that's on the order of 40 to 50 degrees south. So you've got a big atmospheric jet coming out, and you've got an Antarctic circumpolar current in the ocean coming at you. Now, Coriolis in the Southern Ocean, in the Southern Hemisphere, produces things to the left. So this produces drift in the surface towards the equator. And that drift is strongest where the atmospheric jet is strongest. So it's strongest here, and where the zonal winds are weaker, it's smaller. So that says you're getting more water pushed north here than here. So you have convergence of water here, which means water has to go down. If you're getting water coming more and more, water has to go down. The opposite is true south of the Antarctic circumpolar current. Here, the winds are weaker, so you've got smaller equatorward drift than here. So you've got divergence here. The only way to replace that divergence is for water to come up from below. So you have a mean overturning circulation where water is sinking here, coming back down, and rising here. So you've got a clockwise in this plot circulation, and that's what's pulling the isopycnals up towards the surface. Now, as you pull the isopycnals up towards the surface, that increases the potential energy of the flow. And we know that baroclinic instability and the eddies it produces always tries to reduce potential energy. So the eddies are trying to go against what the mean flow is doing and producing a circulation such that you're trying to flatten the isopycnals. So in the Southern Ocean, you've got a mean MOC, which is going this way, and an eddy MOC, which is opposing it and going the other way. And without that extra advection in the temperature equations that we proposed, you miss out the effects of this eddy overturning, which has serious consequences. So here's some of my favorite plots from an old, now 1994 paper that Gökhan produced when he first came to NCAR. This was the first work he did. So we made a comparison of a global ocean solution with very coarse resolution in one where we just used horizontal diffusion, as it used to be, and one where we used the GM advection. So here we go. Now, in the ocean, you have three velocities: zonal, meridional, vertical. If you integrate in the zonal direction, you've got two velocities left: north-south and up-down. And that's what's called the overturning circulation. And because it's just a two-dimensional velocity, we can produce a stream function for it. This is the stream function. And water is going clockwise around positive values here, and anti-clockwise around negative values. So here we've got an overturning circulation, which is in fact all in the North Atlantic. This is the North Atlantic meridional overturning circulation. Strength there of 14 Sverdrups. And here in the Southern Ocean is this mean overturning circulation that I just talked about. forced by the wind forcing over the Southern Ocean. And in fact, you have a counterclockwise, rather strong overturning in the Antarctic to produce too much Antarctic bottom water here. And we know that was too big. Now, when instead of using horizontal diffusion, you use GM, this is the plot you get of the stream function for the mean flow. As you can see, the maximum value is about the same, but larger values are down to the equator of still 12 to 8 spheredrips here, whereas here they've gone down to 8 already. And that was that Veronis effect that I talked about that GM eliminates. You don't short circuit the meridional overturning circulation in the North Atlantic once you get away from horizontal mixing. In the Southern Ocean, you still have this mean overturning circulation like this, which is forced by the mean flow. But if you produce an overturning circulation with not just the mean flow, but the sum of the mean and the eddies, this is the plot you get. It strengthens the meridional overturning in the North Atlantic just a little. But the key area is that the eddy overturning almost completely balances the mean flow overturning in the area of the Antarctic circumpolar current. So this was a pretty surprising result to us that it almost exactly balanced it. But it's important because if you look at a flow like this, at the surface, it is taking cold water near Antarctica and putting it farther equatorward. So you end up producing cold water over warmer water on the north side of the ACC. And that's unstable because the surface water is denser than the water below. So the ocean models doesn't like that. The whole ocean should be stable. So it mixes that extremely quickly. That advection doesn't happen when you've used GM because you're advecting the traces with the mean velocity and the eddy velocity. So that has important implications because when you've used horizontal diffusion, you get this deep mixing here that we've called deep water formation in a large percentage of the Southern Ocean, just because of that reason, that the mean flow is advecting colder water farther equatorward and over warmer water. So the ocean model kicks in with a really, really big value of mixing, and this was the result. To our surprise, when you looked at the equivalent plot with using the GM, you've lost all that, and the only areas where you get deep water formation is in the Greenland Jin Seas, the Greenland, Iceland, Norwegian Seas, the Labrador Sea, the Weddell Sea, and the Ross Sea. And if you went and asked a real oceanographer, someone who doesn't work at NCAR, where deep water occurs in the ocean, they would name those 4 places. It certainly does not occur anywhere compared to something like this. It was this plot that made us realize that GM might make an important difference when it came to climate modeling. I've gone along the first. So the implementation of GM in an ocean component was enabling stable coupled climate model simulations without flux adjustments. Now, we see that from this plot of the paper about the first CSM model. This was published in 96 or 98, something like that. And for the first time, after an initial 10-year period, the integration only went 300 years, you got a stable temperature plot, not only in the land only, but also in the ocean and ice. So if you started with a realistic climate integration, a field of an initial condition which looked like the real climate, and you integrated forward, it stayed similar to the climate. In all climate models before that, if you started with a realistic initial condition, it would quite quickly drift away from that simulation. And the way they fixed that was by cheating, actually. They used these things called flux adjustments. So they found out what fluxes of heat and fresh water the atmospheric component wanted and what the ocean wanted. They subtracted those two, and that was called a flux adjustment, and they implemented that at every time step in the model so that the simulation would keep the realistic look of the climate. This was the first model where that was not necessary. And in fact, nobody at any other climate center believed it. But it was true. And in the years after that, other climate centers put in GM, did some other things as well, and pretty quickly they too could integrate without using flux adjustments. So that's how we know that this parameterization was important in producing much better climate simulations, and as Alice said, in fact, is still used in virtually all climate models that there are. Now, I'm nearly finished, but I can't finish without talking about, in early 2000s, I gave a talk in Limerick in Ireland. Now, it was too much. I couldn't not produce a limerick. So this is how all limericks start. There once was an ocean model called POP, which occasionally used to flop, but eddy advection and much less convection turned it into the cream of the crop. Thank you.
All right. Thank you, Peter. All right, questions?
Thank you for the interesting topic, although I can't understand most of these equations and things. Yeah, and I have a question because I'm doing something related to land atmosphere interaction. I usually run some AMAP simulations using the ocean, just sea surface temperature and prescribed sea ice. And given the sea surface temperature in the coarse resolution and the coarse time resolution also, so how do you think about these AMAP simulation, whether they are reliable? Because you mentioned that coarse resolution ocean can't capture the eddies, something like that.
So if you don't have, if you just use sea surface temperatures, then you're not getting any of the ocean dynamics in.
Yeah.
So that you can use some observations of sea surface temperature about how they change, and that's in fact how you tune an atmospheric model, is you use observed sea surface temperatures. But when you get going, once you've got beyond short time scales, how much heat and whatever the ocean takes up is really important. Remember, it's the most important component. So it starts taking things up. So once you get to sort of seasonal timescales, especially in the tropics, you need that interaction from the ocean to produce the right sea surface temperatures. So if you're going to go out for longer and longer timescales, then you really need an active ocean, unless you then use specifically observations of sea surface temperature that we know about, which in fact you can't do for the future.
So is that means from like maybe from subseasonal to decadal time scale, it can be
Well,
used?
absolutely on decadal. We can have a debate about whether it should be seasonal or whether it should be, well, once you get to a year or less, the ocean is important. Remember that boundary layer varying over that seasonal cycle. Goes from 25 meters to 100 meters. So how much heat and whatever the ocean takes up is really important over that time scale. If you're on weather time scales, doesn't matter.
Another example of that is like Arctic amplification in the atmosphere. If you don't have ocean dynamics turned on, you don't get the right sorts of signals that have been observed for the atmospheric signal in terms of warming at the poles. All right.
Okay, thank you.
Okay, thank you very much for the presentation. Mainly my question related to the deep ocean, how this could affect the mesoscale along time scales.
So the ocean is forced from above. So the mesoscale eddies are much, much stronger in the upper ocean than in the deep ocean. In fact, the eddy energy decreases exponentially as you go down. So this parameterization doesn't do much at all in the deep ocean. It's mostly mean currents that have to go around all the topography and whatever. So eddy effects are very weak there. But it's most important in the Antarctic circumpolar current, and that's where the eddy energy gets deeper because there's so many eddies there. So the eddy energy remains high, deeper in the ocean at the Antarctic circumpolar current than anywhere else.
Okay, thank you.
I have a question about ocean mixing. So we in the paleo community always make this assumption that on the order of the time scale larger than 1,000 years, probably the oceans is already very well mixed. But in most, especially in the end Permian time, the observations we made are from very shallow regions of the Tethys Ocean. So then, and back then too, we know, right, that the ocean gets so hot, the globe gets so hot that some, like the ocean's stratification happened. So then my question is, how and when, I guess, is the assumption that oceans are very well mixed on the order of 1,000 year works and when it doesn't?
So if you're dealing with observation from shallow areas, then it's well mixed because all that action is going on in the upper ocean. It's only once you get down below maybe a kilometer or so that then the equilibrium timescales start to increase. And in fact, that diffusive timescale that Gustavo talked about can be shortened a bit because you do have these overturning circulations in the North Atlantic and in the Antarctic that mix things down quicker than a diffusive timescale. In fact, in the old days with that really old model that Gökhan first put together, we actually once integrated out to see how long it took to get to equilibrium. And in fact, it was on the order of 10,000 years. So the fields in the deep ocean were still drifting very slowly. And it took us 10,000 years before we said the solution was at equilibrium.
And so this is like applies to both isotopic and like temperatures, same thing.
Yep.
All right, who has the next question?
This is unfair.
Question.
He works here.
Thank you, Peter. I know some basic understanding I don't have. How is the bolus velocity derived? What's the concept behind it? Is this kind of eddy U-star velocity?
So if you read that 2011 paper, you'll see that form of the bolus velocity produces a positive definite sink in potential energy. And we know that baroclinic instability reduces the potential energy. So in order to simulate the effects of baroclinic instability, we wanted a positive definite sink of potential energy. So if you put that form into the potential energy equation, you get something which is minus something that's squared. So it's a definite sink of potential energy. So that's how the form was chosen. It wasn't just pulled right out of a hat. It did have some basis, but it's still the basis of all the parameterizations, and the various parameterizations that are used in all the different models across the climate. It's the specification of how you specify that parameter, kappa, that changes. People do that in all sorts of different ways. We have it such that kappa is much stronger in the upper ocean, where the eddies are much more active than in the deeper ocean. So it's in the 20 or whatever years since, there's been enormous numbers of people proposing different forms for that coefficient kappa. But the basic form of the U star from those density gradients has always stayed the same.
Thank you, Peter. Very impressive talk. I have a small question about at the beginning you talk about the Richard number, the equation. It's like buoyancy divided by the wind shear, but in the denominator there is an extra term in addition to the wind shear. Is like interior something. Can you talk about more about that?
Yeah, that's because in the resolution we're not resolving it very well. So that if you went to higher and higher resolution, you'd get a bigger and bigger vertical shear of the velocity. So if you can get situations where the velocity doesn't change very much in the vertical, and so that Richardson number starts to get larger and larger and larger. It can actually go to infinity if those two velocities at the surface and the depth d are the same. So we put that extra term in there to ensure that that was due to unresolved turbulence, such that the Richardson number didn't get too large and blow out. But in general, the resolved velocity shear is actually larger than that value. So.
All right, who's next?
Thank you, Peter. Thank you for creating the GM parameterization for us. Yeah. Can you give a perspective of the application of machine learning in ocean parameterization?
Of what?
The prospect of the application of machine learning in the ocean parameterization.
What do you think about machine learning for ocean parameterization?
I don't think about it very much at all. I'm retired, but Gustavo is going to answer this question.
So Peter mentioned that kappa GM is, a lot of people have proposed different ways of computing kappa GM. But now machine learning, using machine learning is one way of computing kappa GM, and people are pursuing an approach where, given the resolved scales in the model, like, can we estimate kappa GM throughout the water column that gives minimizes the errors in the model. So that's one example. People are also using within the vertical mixing. Peter didn't go into details, but there's a lot of shape functions that are used to match surface from interior diffusivities. And those were done many years ago with cubic functions, but now people are relying on machine learning to do these adjustments. But I'm happy to talk more about other ones if you're interested.
All right, are there any last burning questions?
Hi. So today I'm learning that the ocean is the most important part of the model.
She got the takeaway point, Peter.
So I'm actually wondering.
You can't be disputing that.
So when is it appropriate then to use a slab ocean model? Because isn't that where we take out all the ocean dynamics, and that would be taken out an important part of the model? When is it appropriate to use a slab ocean model, or should we start avoiding that entirely as our modeling is more advancing?
I've never used the slab ocean model.
I know other people do, and it
the
seems
ocean
wrong,
dynamics,
so
so
I'm
it's
wondering.
almost never used by people in the ocean section. It, again, is, I talked about the answer to the first question. For atmospheric stuff, you can use prescribed sea surface temperatures. If you want to go one step beyond that and resolve how much heat is going in and out of the ocean over an annual cycle, then you can use that slab ocean model, because it'll give you that, excuse me, it'll take heat up during the summer, store it in the ocean for a bit, and let it back out again over the year. So it's the next best, well, slight improvement, not best, slight improvement over using just sea surface temperatures. But again, if you get then beyond timescales of a year, once you're at decadal, for instance, I don't think you can believe what's going on. So I've always avoided it.
Thank you.
If you have more questions about the slab ocean model, which Peter recommends avoiding, but sometimes is needed because we've talked about you have to balance the resources you need for your experiments with what your science question is. So if you have particular types of science questions, it might be appropriate to use it. Dave Bailey, who gave the sea ice talk yesterday, and he'll be here this afternoon for the practical session and tomorrow for the challenge exercises, I think he put together an FAQ, like frequently asked questions about the slab ocean model, and he might be able to answer other questions.
So Alice is always a much nicer person than I am, so she gives nice controlled answers.
All right. So with that, we're going to go ahead and have a break. There's food at this break, double line again. We have it in the middle of the room. And we'll see you back here at 10:30 for some special lectures about tuning and coupling and climate variability. hopefully you guys had a good break there. The next session, instead of doing a practical, we have a couple of specialized lectures. So the first one is going to be by Cecile, who you guys have seen throughout the week. And she's going to talk to you about the kind of the behind the scenes, how you actually make it work in terms of the tuning and coupling of a model, which is something we run into all the time.
Yeah, okay. Okay, then I want to a little bit demystify the building of CSM, the model that you are using. Then basically this is the outline of what we are going to talk about. I'm going to give you a brief timeline how we built CSM2, the model that you are using right now. And then I will talk about the art of tuning and some tale of coupling. And you will see why I have this little picture over here. Okay, then the timeline of building CSM2. Then this is an effort that started in 2010. And then, yeah, I don't know, maybe you were even in kindergarten at the time. But it started a while ago. And then we started by building the individual component. Every working group was working and building the individual component. What does it mean? For example, for the atmosphere, we were focusing on aspects of the model that we wanted to improve. That this is the atmosphere we are pumping. And then we had looked a lot at changing the dynamical core and the resolution of the model. Also, we looked at improving some physical parameterization. And during this phase, we did a lot of uncoupled simulation. We just run the atmospheric model alone, and we look at plot and we do analysis. Then we did a lot of this. And all the other components that you are seeing in the model, they did this too. Then it took 5 years really to build this phase. After this 5 years, we started to put everything together. And we saw it will go really fast, but there were a lot of setbacks. Then it took, at the end, 3 years before the release. Then we started in 2015. We had like a lot of meetings with everybody. It means all the co-chair talking together and all the liaison. We did about 300 configurations that we were testing, and we had thousands of simulated here and diagnostic. And at the end, we had the CSM2 release in June 2018. And it was the one that you are using now, and it's the one that was used for the IPCC. Then you see that at the end, this timeline between the start and the finish, it took about 8 years to build the model. And along the way, there were a lot of tuning and coupling. And then I'm going to talk about the art of tuning, and you are going to understand why I call this art. Then what is tuning? People, it's something, I started to talk about tuning because it's something that's a little bit mystifying. People say, what are you doing when you tune the model? Then when we tune the model, we adjust parameter in the model, what we call tuning knob, to achieve the best agreement with observation. Then when I say tuning knob, or this parameter, it's parameters that are weakly constrained by observation. I'm not going to tune gravity. This is, we know what, yeah, just like, an example, sometimes it's even variable parameter that don't really exist. It's something that's put in the model, but it's not really exist in real life. And an example, it's something that we saw in the lab yesterday. We adjust DCS. It's the threshold diameter to convert cloud ice particle to snow. And I'm going to explain a little bit what it is. Then you have cirrus cloud. It's the clouds that are very thin, very high on the atmosphere at altitude higher than 5 kilometers. And they're basically made of ice crystal, what we call cloud ice. And you have your little representation of cloud with all this little ice crystal. And when you have a cloud like this in the model, the big ice crystal are going to fall off the cloud. And it's what we call when the cloud ice convert to snow. When there are some size, we say that it converts to snow, and then it just fall out of the grid box. And it's what we call the threshold diameter. And this DCS parameter that we were talking about yesterday, this is this parameter. When the ice cloud, the cloud ice are bigger than this, they just fall off the cloud. Then what's the impact on the climate? Then I have here two representations of cloud, with this one with smaller DCS and this one with larger DCS. Then with the smaller DCS, all the big ice particles have fall off, and this one is more ice clad. This one is less clad ice. And what's the impact on the climate? Then indeed, when you have smaller DCS, you will have the infrared radiation will be able to go out to the space more easily than in a cloud with larger DCS. Then if you have more cloud ice, you have less infrared radiation going out back to the space. Then this is the impact on the climate. Then when I say that now the second part, it's to achieve best agreement with observation. And this is here the energy budget. And this is where my DCS is applying. Then you have the infrared radiation. And when I adjust DCS in my model, basically I'm adjusting this parameter. And why do we want to adjust things like this? It's that, for example, something very important when you do a climate simulation, it's that the top of atmosphere radiative balance should be close to 0. We know that the Earth is more or less in radiative balance. And why is it so important to tune this, to adjust this in your climate model? And this is a simulation, an example. In this case, my radiative balance is larger than 0. It's about 3 watts. It goes down a little bit, but it adjusts about 1 watt. And the corresponding temperature of the ocean is going to warm, because basically when you put some heat in your system, and then the ocean, it has nowhere to go in the atmosphere because the atmosphere is such a low heat capacity, then everything goes in the ocean and the climate simulation is going to warm. The ocean is going to warm. Then it's why it's important to adjust the top of the atmosphere radiative balance in your climate simulation. Otherwise, you will have a running away simulation. Then this is one parameter that's very important in coupled simulation. We have as a target when we are tuning, we are looking at the cloud forcing, precipitation, and so AMOC, the sea ice thickness and extent, and it's not the only parameter. But we are looking at all of this and even other stuff when we do the tuning of the model. And then tuning, it's where I say now it's the art. There is dilemma. Then first there is the subjectivity of tuning target. Then when you tune, you cannot have everything right. Then it always involves choice and compromise. But the good news is that overall, the tuning has limited effect on the model scale. If you choose to adjust a little parameter instead of another one, at the end of the day, the model scale are very similar. Another thing, then do you tune in a pre-industrial simulation or do you tune for present day? For pre-industrial, it's, you know that pre-industrial, it's the type of simulation you are doing right now. You have really a radiative equilibrium, but for present day, you have available observation. Then in our case, we tune the first one, but as a center, tune the second one. Also, do you tune individual component or in couple mode? And when you tune individual component, it's very fast. You can do a lot of simulation, but there is no guarantee that it will transfer to the couple model. And I'm going to show some example of this. And then the last thing is that it takes quite a while of tuning, but it's a tuning exercise is very educative. While you are doing this, you learn a lot about the model during this tuning phase. This is what I wanted to demystify a little bit about tuning. The last thing is the art of coupling. It's when we put everything together. And what I call this, when you are doing coupling everything, I call this unleashing the beast. Then basically, when you do standalone simulation, if I do, for example, a simulation just with the atmosphere, it's what we call AMIP type simulation. It's a type of run where the sea surface temperature are prescribed. Then the model, you prescribe the sea surface temperature, then even, for example, if your radiative imbalance is not close to 0, your model cannot go anywhere. It's really well behaved. Once you put the full active ocean, then you have a lot of couple bias and feedback, And then it's when this is happening. People always ask me, where do you get all these cartoons? Then my husband, who is a physicist, like also to draw cartoons, and I always ask him, oh, can you draw this? I want to show this in my talk. And it's why I have all this little cartoon that's always well adapted to the situation. But anyway, this is, coupling is really unleashing the beast. Then I'm going to show you 3 examples of problems that we had during the development of CSM. And there are several versions of the model. The first example that I want to show you, it's when we were developing CSM1. It's the version of the couple model before the one you are using. And at the time, we did all our tuning in EMIC mode. And we had really a perfect simulation. We were so proud. We had really improved the climate. We were really excited. And then we put stuff in couple mode, and I show you unleashing the beast. And this is what happened. This is the evolution of the SST error over 12 years. Then when it's blue here, it means it's bad. Then after 1 year, we had already very large bias. And then after year 2, it started to build. Here it's another kind, mean SST error. It was huge, mean SST error in the North Pacific. And then what was happening with this, it was really bad because what was happening, we had colder SST in the North Pacific. It had an impact, we had more cloud because of this colder SST, because we had more low cloud, we had more SST were even cooling further. And then because of this, the sea ice started to grow. And then because the sea ice grew, we had even colder SST, then it was just the simulation turned bad within 12 years. And it's when I talk about unleashing the beast. And then at the end, what we did, we had this perfect simulation, and we had to do the compromise to make it less perfect, that it's not a runaway simulation. Second example, it's when we tried to change the dicot. And it was again in CSM1. We wanted to go from the finite volume dicot, that's a Latland grid, it's still the one that you are using, and we wanted to go to the spectral element dicot. It will be the one that will be in CSM3. And then there are a lot of advantages of doing this type, the other dicot on the right side. But when we did this, we had also, sorry, this is a problem with, sorry for the font here. It's the transfer between Google Slide and PowerPoint. Then when we, once again, we did everything in CAM standalone, like we didn't learn our lesson from the first time. And in CAM standalone, when we did the finite volume and the spectral element, the simulation were almost the same. It was even boring. It was just, we changed the dicot, and it was not changing almost anything. The difference is the almost. And then when we put in couple mode, then suddenly this is the sea surface temperature in couple mode, and you see that the model is cooling by half a degree after about 40 years. And this was a showstopper, then we were not able to use this dynamical core. And what was happening here, we look a lot, we could not understand why there were this difference. And the difference, it was here you look at the zonal surface stress, and the maximum in the spectral element dicot moved north by just a little bit, tiny. But then the problem, it was in this very important location, the upwelling zone, and associated with this, the ocean circulation, this very slight difference was responsible of the SST cooling. Then it was another example of unleashing the beast. The last thing that we had more recently in CSM2, and we are also having problem in CSM3 with this, it's that the Labrador Sea was freezing in the development of CSM2. Then this is here a view of the sea ice. You are looking at the planet from the top. And the Black Sea here show the sea ice extend. And the Labrador Sea, it's this area that's over here, and you see that in the observation, the black line, you don't have ice here. The Labrador Sea is basically ice-free. Now, if you look, when we did this CSM2 development simulation, then you see that it's not ice-free, it was covered with sea ice. And this was happening sometimes after 1 year, sometimes after 40 years, and sometimes after 100 years, which was very tricky to find how to fix. And we figure out what was happening. Then basically in CSM1, we had a bias. It was too warm and too salty in this area. While in CSM2, it was too cold and too fresh. And this is just the bias or the direction. At the end, this one was not much worse than the other one. But the problem, when we were too cold and too fresh, it was not helping with the Labrador Sea freezing, while this one was helping for the Labrador Sea not freezing. Then this is, I hope I convince you here that when you do this coupling, you can get a lot of surprise, and it's what I call unleashing the beast. Then in summary, then I show you that building CSM2 happened in two phases. We built all the components, and after we couple everything together, and between the start and the finish, it was about 8 years. Then it takes time and a lot of people involved into this, and I hope you will get involved too. And then I talk about the art of tuning, then it's adjusting parameter to achieve best agreement with observation. And then we show that it involves choice and compromise, but we learn a lot about model tuning and also the art of coupling. I show you 3 examples that we had during model development, 3 coupling challenge. Okay, this is, yeah, I think I start time.
All right. Thanks again, Cecile.
Thank you for the excellent presentation. So yesterday we worked on the change on DCS, like how the larger and smaller particle affects the simulation. So my question is, like, if we want to make more customizations, for example, I want to see the doubling of CO2 in the atmosphere or quadrupling the CO2 concentration in the atmosphere. Is it as straightforward as yesterday's, or it's like we have to go through more further changes to the source code?
Yeah, then when you do, this is not tuning, then when you are going to change, for example, you are going to double CO2 or change SST plus 2K or something like this, then it's a forcing, you are going to change the file that you apply to the model. And it's not, yeah, it's fairly easy to do. While here we are changing something inside the structure of the model when you are changing DCS. Does this answer your question? Yeah.
Thank you.
Yeah.
I'm wondering how this tuning of the model for present day or PI control simulations affects the applicability of the model for paleoclimate.
Sorry,
how does this tuning of the model to match present day observations affect how usable the model is for paleoclimate simulations?
Yeah, then this is a tricky part, because what you do, when you do the paleoclimate, sometimes they are surprised. We had, for example, issue recently. We had tuned the model. We had tuned some parameter, but then when they look at the last millennium simulation, they were negative impact, and they choose to tune it a different way. But we didn't know before. We cannot do all the simulation when we do the tuning, when we develop the model. Then you have a version, and then after, when we release the model, they do the longer simulation. But then there were a lot of effort, and one of the person redid a different type of tuning that was helping his simulation to be better in the paleoclimate. Then you don't know before you do it, but there is an impact for sure. Yeah.
Hi, thanks. I'm mostly curious about whether or not, when you show this list of essentially tuning targets, if there's any kind of process that goes into identifying the components of the system that we use as tuning targets. So like, why do these things make it on this list versus any other component?
Yeah, then this is really, again, it's a little bit a matter of compromise and a matter of choice. This is what our scientists here consider really important. You would have different modeling group that will not put the same impact on the same. not every modeling group have the same list of parameters. And it's really after discussion with the scientists and what they really believe. This is a showstopper. We cannot have precipitation that looks like this because it's bad. This is the way that we have picked this list of targets. But as a modeling center will not have exactly the same list. It's really what we consider the most important because you have to make choice. You cannot get, we would like to get everything right, but usually it's not possible. Then we are focusing really on some stuff that we say, if you don't get this right, we cannot continue the simulation.
I can say from sea ice experience that some modeling centers submit their CMIP runs and like all the sea ice goes away or it's like hugely extensive. And for us, that's a showstopper, but I guess for them, that's less important. Maybe that's not their primary thing.
Yeah.
Next question here.
Hi, Sissy. Thanks for your presentation. My questions are, one, why do you think that tuning parameters has limited effects on model skill? And two, as far as I know, there's another way to improve the model skill is to add or remove processes to the model so that it can incorporate that. Then can you compare with that approach?
Yeah, then when I say that it has limited scale, what we have done in the past, we have had effort and we tune things different way. When I say it has limited effect, I don't say that it has no effect. I was giving an example that on the paleoclimate, it had an effect. It has an effect. The choice of tuning parameter that you pick has an effect. But we had like people that did a group of simulation where they try different tuning, and at the end, the model scale, we have like some diagnostic that show if the model is improved, what we call the Taylor diagram, for example. Then this is a set, it's a metric that show if the model is improved or not. And the different type of tuning didn't have, the overall performance of the model would be similar. And it's why when I say it has limited effect, I don't say it has no effect, it has an effect, but it has limited effect. It's not going to throw us in the category bad IPCC model or good IPCC model. They will be the two. Then the second way, developing, adding process, it's when we are trying to develop parameterization. I was showing, sorry, just go. Okay, then this is also something we want sometimes to develop new parameterization, to add new process to do better. But this is a little bit a different effort. When you do this can take, you can spend your life to develop new parameterization. At some point, you want to release a version of the model, and you cannot fix everything by adding process in your model. Then you will have to adjust some parameter in the model to, even if you know that it's not, there is room to add more process, but you will have to adjust some parameter to make it closer to observation. Then, for example, for a long time, we didn't have the indirect effect in the model. It's not that we didn't believe in the indirect effect, but we didn't have the microphysics that was necessary to do the indirect effect. And after in CSM2, then, or CSM1, I don't remember when they add this microphysics. Then they add the microphysics that was necessary to represent the indirect effect, and we add this. But before we didn't have the physical parameterization to represent it. But this is something that we want always to improve. But at some point, we need to give a model to the community, then we release it.
Yeah, so it's a nice talk. I have a query regarding the warming issue in the CMIP6 models, basically. So do you think that, what I believe is, I think all of the modeling agency definitely like looking into the top of the atmosphere radiative forcing balance. So even that in that scenario, in a, let's say, double CO2 condition, why some models are warmer than the others? So it's coming from the lack of parameterization representation, or what's your comment on that? So even though the top of the radiative balance is 0, still for a particular forcing, why some models are warmer
Yeah,
than the
then
other.
this is the climate sensitivity of the model.
Yeah.
Then you adjust the model. Our model is a pretty high climate sensitivity compared to the pact of the CSM CMIP6 model. But this is, I need to adjust. Let me check if I can. At some point, I want to adjust this radiative balance. I want to be closer to this, but there are a lot of the climate sensitivity is not coming from this top of radiative imbalance. It's come from all the process that I have in my model, and it's what's going to be different from one model to another.
But there must be a condition like after some time there will be a radiative equilibrium in the new climate. Let's say you are putting some force in the model. So maybe after some time period, it will be a new radiative equilibrium, right? Instead of the present one. Let's say there is a model and we are forcing something, then after some time, it will reach to a new radiative equilibrium.
Yeah, but it takes a long time.
Yeah.
This is the problem. It takes a long time to reach the radiative equilibrium. And sometimes you have warmed the ocean. If I start with a radiative balance that like this, if I wait 10,000 years, it will be adjusting. It's going to adjust slowly, but then the ocean will be way too warm and the oceanography, the sea ice will be probably gone. It's just that you need to start with a simulation. It's true that if you wait, you are going to send back more long-wave radiation back to the space, and at some point it's going to adjust. But by that time, your best simulation will look bad. And I see that Clara, your neighbor, maybe has a comment. She's a famous scientist here. Yeah. Okay, no.
In line with.
Thanks. I'm fascinated by the, I guess, the logistics of the coupled tuning process. And we've been hearing all week about major updates to individual components, like the change in the dicore in the atmosphere and the switch from pop to mom. Are each of those individual teams responsible for doing their own coupled tuning experiments? Or is this something where they complete development of an update to a component and then couple the model and perform tuning experiments?
Yeah, then this is really a mix. It's a good question, and it's a mix of both. For a long time, we were really doing most of the tuning in the individual component. And there's still a lot of tuning that you do in the individual component. When I'm talking about the DCS, I know that the ice particles that are falling off of the model, they are not like 1 meter or 1 yard. I know that they are between like 200 micron and 500 micron. And I know that we adjust some parameter. But then the problem, and it's what I was showing before, we did like simulation like this when we do all the tuning before putting in couple, and then when we put in couple, we have like big surprise. And it's why now we have changed the way, especially the model become more and more sensitive and more complicated. We changed the way that we don't wait forever before we do a couple simulation. Right now, we spent last summer with Gustavo, he's the ocean liaison and I'm the atmospheric liaison. And we did like this new vertical resolution for CSM3, and we changed the dicore, and they were using a new pop model. And we spent like several months to do an intermediate assessment to make sure that when we are going to change, it's not like a big surprise. And they were a big surprise because the Labrador Sea froze again, and it's just like, then they were, but we do now more. Before what I was showing here, we were really, we were really doing phase 1 and phase 2. I think it's here on this plot. We were really doing phase 1, we will build, and then after we will couple. But now we do more this, and then we go a little bit couple, and then we come back to this, and we do along the road several coupling. Because we as the model become more complex, there were more issues when we will do the coupling. then they are part of the tuning that we do in the couple. But the problem when you do something in couple, everything is more expensive. For example, if the atmosphere is already pretty expensive, then I do couple or standalone, it's okay. But the land, they can do thousands of years if they just run the land. If they start to want to do the tuning of the land in couple mode, it would be really bad. I guess for the sea ice, I never run the sea ice alone, but I guess it would be the same simulation, the same issue.
The sea ice is way cheaper than the atmosphere.
Yeah. Then if she wanted to do everything in couple, then it would be very expensive. But at some point, you have to do it in couple. But then it's really like a mix of, now we don't do this linear thing. We do like, we are here and then we go here. It's more like now for CSM3, we have done more this back and forwards.
All right, we're going to take one last question while I switch the slides here, and then we'll move on to the next specialized talk.
Okay, my question is about the radiation balance. So do we have all the information that's happening in the outer space? Like, for example, if I'm running the global model for over 30 years, these solar flares happen every now and then. We don't have the prediction capability, but we observe them. So do they have any significant impact on running a global model for over that period of time in the imbalance of the radiation?
Yeah, the imbalance of the radiation, in the observation when they do the global radiation imbalance that are coming from observation, this is not really easy for them. If they just do observation and they don't do any readjustment, they will have a radiative imbalance that would be, I don't remember which way it goes, but it will be not close to zero. Then they do a lot of adjustment on the observation to have radiative balance that we know it's close to what we know the radiative balance is, what we believe the radiative balance is.
All right.
Then 0.6 or watt per meter square.
Okay. Well, as you can see, this is a really complicated topic, and we probably could literally talk for more than an entire day on it. But we're going to go ahead and move on to our next specialized lecture here. Okay, it's on now. I'm just kind of pin it here. Okay, so our next speaker is Clara Desser. She's a senior scientist, and she's the head of the climate analysis section. She studies climate variability and change in both observations and models, and she's done an awful lot for improving our understanding of internal climate variability and the importance of using large ensembles for better understanding that. She's also a member of the National Academy of Sciences, a fellow of AGU and AMS, and she likes hiking and cooking and playing piano.
That is such an old thing, but I still do those things. Very nice to see everybody, and it's a pleasure to be here and to see all of you. I was not in kindergarten in 2010, I can assure you, so it's wonderful to see everyone. My talk follows very naturally from Cecile's presentation. You know, how do you achieve agreement with, between your model and observations? And it's actually very nuanced and topic when it comes to climate variability, and that's what I want to highlight today. So how do we evaluate the variability in the model, not just the mean state, but the variability? And I'll present what I think are some main challenges, and then give you some tools that we have here at NCAR that can help to address some of those challenges. So in my view, the two biggest challenges are, number one, we have limited sampling in our observational data sets. Even if you have, sea surface temperature measurements over 150 years, that actually still doesn't give you a accurate or precise representation of the full range of variability that the real climate system could undergo. So you always have to be very aware of, the limitations of due to the length of record. We don't really have that problem in models, as you will see in a moment. And then now we are very much in this age of climate change, and we can't ignore that, and that is going to affect our climate variability. And so when we even try to isolate variability in a climate that has some background climate change that is accelerating, you have to then find good ways to take account of that evolving forced climate change signal and remove it to really get at the internally generated variability. And this is still a very much active area of work, and I think it's incredibly important. So the new tools that I want to highlight today are first these so-called large ensembles of simulations. And these are with a given model and a given forcing protocol. So these are just lots of simulations with one model and one forcing protocol, and then that can be repeated with different models. And the other tool that I want to highlight is a tool that Adam Phillips and I have led the development of with input from so many people, and that is what we call the NCAR Climate Variability Diagnostics Package, and a new package specifically for large ensembles. And as Alice and Cecile well know, this package played, I think, an important role in the development of CESM 1 and 2, or 2, I guess, because we were tasked as the climate analysis section and knowing a lot about the observed climate variability. How do we tell if the model's ENSO is realistic? And that was one of the targets on Cecile's list. I think it very much belongs on that list since ENSO is so important for global climate. And it's, again, you'll see you cannot give a perfect answer to that question of how well the model is doing in terms of its representation of ENSO. Okay, so what are, Flavio Lehner, I think, gave this very nice acronym, SMILES, for this single model initial condition large ensembles. So I'll just explain what that is. So we're dealing with global coupled models like CESM2, typically 1 to 2 degrees latitude, longitude, spatial resolution, but it can be any resolution, of course. And initial condition simply refers to the fact that you can run a lot of simulations with the model with the same forcing, but you just perturb the starting point of the model by tiny amounts. You don't have to perturb it much. And then that can set off this chaotic climate system in a different direction from one simulation to the next. So I do want to highlight that these initial condition large ensembles, I view them as they can be free running. So the whole climate system is just being, you're applying some kind of forcing and you're then letting it run. Or you can partially constrain the coupled model in a particular region. So for example, it's called this pacemaker protocol. So you may want to know, okay, if I'm interested in how ENSO affects global climate, and I want to constrain my ENSO to be from observations, I can nudge the model's SSTs to the observed SST evolution, and then I can launch a lot of simulations, and I'll show you an example for that. So I consider these single model initial condition large ensembles to be either fully free running, I think that's what we all typically think about, but I think this partially constrained pacemaker protocol is also a subset of these SMILES. So the salient features, that is obviously large ensemble size, and how large is large enough is, again, not one size fits all. There are lots of papers written about, depending on your target, how many ensemble members you need to really have a very good assessment of the noise, the climate variability in the system and make sure that you are spanning the full range of possibilities. So typically I think of large enough as being, somewhere towards 100 simulations. And so you have different initial conditions for each simulation, same forcing protocol for each simulation. And that could be this emissions scenario or pacemaker constraint. So then in a nutshell, that means that each simulation can follow a different random sequence of internally generated variability, and that's superimposed upon a common forced response after the memory of the initial conditions is lost. So how do you assess this in climate models? It's very simple math. If you have enough members, that forced response at any given location is a function of time. You can estimate with the ensemble mean of the simulations, because that random variability is phased differently in each model, in each simulation, so they should eventually average out. And then if you subtract that forced response from each individual simulation, then you can isolate the internal variability. So it's easy enough in models, it's very difficult in observations. So just to hit it home, lots of samples of internal variability, and this is crucial for robust estimation of the evolving characteristics of the forced response. I think until we had on these less than global scales, and I think until we had large ensembles, we were sort of mischaracterizing things or misinterpreting some things. And I really want to emphasize that the forced response has two components. One is the background climate change. Okay, it's getting warmer, it's getting wetter. But the variability that is happening within the atmosphere and between the ocean and the atmosphere, that variability, which exists in the absence of forcing change or forcing, that can be affected by the forcing, radiative forcing as well. So the force response really has these two components, changes in the background climate and changes in variability. So ENSO may amplify or change its spatial extent in the future, and that has, of course, really important consequences. So I think the second point is now really being dug into by the community as we have these large ensembles to work with. So if you're interested in more reading, I would point you to a paper by a working group that I co-led, U.S. Clybar Working Group on Large Ensembles, and this was a paper that really tried to collect, just to communicate what these are and what they're useful for. And then if you're interested, we are now very much, community-minded. So we have, as part of this working group, we have collected a subset of model output, the sort of typical fields that one might analyze, and we've put them on this, you can access them via this web page here. And so it makes it very easy to work with. You don't have to go find them yourself, it's all there. And you can just, it's as if you're looking at the CMIP archive. But these are large ensembles with available CMIP5 and CMIP6 models. And we are very close to releasing or an expanded version of this archive or resource. And that will encompass 16 models. And remember, each one has between 30 and 100 simulations. So it's a really amazing resource. And we are expanding it to 11 different output fields or variables. And that will be coming soon. And that's very much credit to Nicola Maher. So I point you to that resource as well. So now I'd like to just give a couple of examples of this, and then I'll turn to the diagnostics package. I know we started a little late, so if you don't mind, yeah. Okay, so I'll pick two examples. They come from work that I was led, but I could have chosen different examples, but I'm most familiar with these, of course. So the first are ENSO teleconnections. And you know, again, coming back to Cecile's talk, you want to have agreement between your model with observations. And then the question is, well, how well do we know Enso-Tele connections? And then how do we evaluate models accordingly? And I have to say, this paper really came about simply because we had this pacemaker protocol of simulations for the tropical Pacific. And one day we plotted them all up and said, why are they so different? So this was the beginning of a paper, and it was really spurred by this kind of large ensemble protocol plus the diagnostics package. So what we're going to show you here are it was from CESM1. We have a similar now set from CESM2. You're welcome, of course, to look at any of those data. So these are 10 realizations or simulations with CESM1 for the time period 1920 to 2013 under historical radiative forcing evolution. And then the important thing here is that we ask, the model has biases in its ENSO SST variability. So we're interested in, okay, let's nudge the model's SST anomalies, so not the mean state, but the deviations from the mean state to the observed SST evolution in the tropical Pacific. And then we can look at how the atmosphere and the coupled ocean atmosphere response outside of the tropical Pacific, what that looks like and how well the model represents that. So it's the model's response to the observed SST evolution in the tropical Pacific. So if you're familiar, just back up here. So what I'll show you is a northern boreal winter composite of sea level pressure. That's a typical way of looking at teleconnection patterns. And we will composite. There are 18 El Nino events during this time period and 14 La Nina events. So that's a lot of samples. And I would expect we know the teleconnections quite well with that number of events. And I was wrong. So here is, I'm going to end up showing you all 10 simulations, but here is number 7. And you're looking down on the North Pole, and the Pacific, North Pacific is to the top, and the North Atlantic is sort of down at to the southwest there. So this is, and where you see color, that means there is a significant sea level pressure teleconnection. So this is what we expect, this deepening of the Aleutian low. That is the hallmark of wintertime ENSO teleconnections. So that looked very, very good. And here's another of the simulations. The same observed SSTs, the same collection of El Nino and La Nina events. And lo and behold, you still get the deepening of the Aleutian low. You better, otherwise, your Rossby waves in the atmosphere are really not represented correctly. But then you get a strong NAO-like response. Which one is right? If we're gonna compare with observations, now what? It's all now opens a huge can of worms. And here's all 10, just to give you the sense of there's definitely the Aleutian low is in common, but the amplitude of the Aleutian low response is different or varies. And this Atlantic NAO kind of connection comes and goes. And these are observed SSTs, the same events, it's the same model. And we had 2 other modeling centers repeat these, and I can assure you it has the same kind of diversity. So here's the observed composite, same events as we're using in the model. Okay, it looks, some things are similar, some things are different. So model agreement with observations becomes a very nuanced question. So the questions are, how well do we know the observed composite? The only reason why each of these simulations is different is because there's some unforced variability in the atmosphere that is imprinting on the actual forced ENSO teleconnection. So how well do we know the observed composite? This paper goes on to really address that question. I don't have time to do that here. And then, for the purpose here, how do we evaluate the model? And that can be broken down into two subsets, sub-questions. Is this kind of spread in the model realistic? And that's only due to internal variability that is not driven by ENSO. And then is the true response to ENSO realistic? And that's a really hard question to answer because observations, unless we have some paleoclimate proxies that really help us, we really can't really say what is the true response. So I was very surprised about this. Okay, quickly, another example, and then on to the diagnostics package. So we've talked about variability of ENSO. That's 1 year to the next. This same conundrum also happens for longer-term trends. So the example of the North Atlantic oscillations. So here, I will show you from the CESM1 large ensemble. This is free running, not constrained, not a pacemaker. It's free running. And I think probably you're all familiar. It's this historical and RCP 8.5 forcing out to 2100. So I'll just show you two maps that, again, open my eyes. So I'm going to show you maps of the sea level pressure trends projected for the next 30 years from this ensemble for the North Atlantic region and how it impacts temperature and rainfall. So how well can we project climate going forward? So I'm picking out simulation 13 and 25 to make my point here. And the sea level pressure contours are contoured there. And I've put the plus and minus sign to show you what the trends are for the next 30 years. And then on land here, you're seeing the air temperature. And lo and behold, the trends in the NAO, or the sea level pressure dipole, are largely equal and opposite between the two. Which one are we going to get? That is, unless there's some predictability in initial conditions that really, gives us information, memory out 30 years, which I don't think is the case, we are faced with this kind of, I don't like to call it uncertainty, but it is the true, well, it's a model here, but I'll say it's the true character of the climate system, that it has a lot of variability, even if you're adding forcing. And you can see that the temperature projections, especially for Northern Europe, can be vastly different, even though you're giving it the same increase in greenhouse gases because of this circulation effect. And this is precipitation. You can just see that the precipitation is also very different. Okay, last 5 minutes. This is a tool that I personally have found extremely valuable for research directions, and we are continuing to improve it. And I hope that some of you will find it useful, and we're very interested in feedback also on this tool. So this is an automated tool. You don't have to know how it was built or the language or anything. And it's an automated analysis tool, and it's a data repository for exploring these questions of forced and internal components of climate variability and change. So some sample questions that you might use this package for: how well does a given model simulate mean state, long-term trends, and modes of variability? We have lots of modes of variability in the package. And again, now with background that I've given you, it's not a simple answer, right? You have to really pay attention to whether you have enough samples of your data to really be able to assess how well the model does. And then you can compare one model with another, and you can really then address whether the models are truly different in their representation, say, of ENSO, or whether it's just a sampling issue. You can look at how climate change affects variability. And then this last question about the relative contributions of internal variability and forced climate change to long-term trends. And I really just want to hammer this home because a lot of papers do not do this. The null hypothesis, right? We have to beat the null hypothesis, is that any apparent model bias, any model difference, and any model projected change in variability, the null hypothesis is that it's just due to inadequate sampling, or what we call sampling fluctuations. And if you can negate or refute the null hypothesis, then you can go forward. But this is the null hypothesis. And you may see an apparent change, and so in the real world looks like it's getting more variable. We do not at all know that that is due to forcing. We do not know that. In fact, we can refute that. we cannot refute this null hypothesis. So I'll just walk you through, and then I will end. So it does a lot of computations, and then you get the data from the repository, and then you can analyze them further. So you don't have to do EOF analysis. You don't have to do a lot of this stuff. It's provided. We give quantitative comparison to observations, look at ensemble mean and ensemble spread. I wrote a lengthy user's guide to really try to give information about it. And you specify the data sets and the time periods, any collection of models, observations, different time periods, you name it. Adam has made it incredibly versatile so that you can really do a lot with a package. And again, all output is saved to a data repository. So this is what it looks like if you go to the page, and this is the type of interface that you'll see. And you get a bunch of variables, et cetera, lots of different seasons. This is climatological averages. You click on that, you get the maps, or you get, and then behind that, you get the net CDF files. So we compute means, maps of standard deviations, so variability, long-term trends, depending on what, for the time period that you specify. We really emphasize the coupled modes of variability. So lots of diagnostics on ENSO, on Atlantic multi-decadal variability, Pacific decadal variability, and AMOC. Lots of atmospheric modes. So those familiar with these acronyms, you'll recognize them. And this is all subjective choice. We wanted to limit the number of modes calculated, but also wanted to give enough that it was be useful. And then we have a bunch of time series. And then we have also a dedicated part for sea ice. And then I'll just give you a flavor for the output. So this is for the NAO pattern, and this is from the Max Planck Institute model. 70 members were used, and this is the model's representation across all 70 members of the NAO, the observations in the second row, and then the difference. And then the last row is the new thing. Does your observed NAO amplitude fall within the spread of the ensemble? That is the primary thing for evaluating the model. If it lies outside, your model does not represent it. If it doesn't match a single member, you cannot say that it is poorly represented in the model. But it has to lie within the spread, and that is the key feature. Here's the same thing for CSM1, and again, you can have different numbers of members because we're looking at percentiles for the rank. So the number of members, precise number doesn't matter too much. So here on the lower right, it is very clear that these bright colors, that's when the observed NAO lies outside any single simulation. So CSM1 is a lot worse than MPI, and you can say that with confidence for the NAO. a little more eye candy, this would be computing pattern correlations between the observed NAO and each member of a large ensemble, and lots of spread. So if you only had one simulation, you do not know where you fall on that range. So you do not know how well the model is simulating variability. And then you can assess observational uncertainty by supplying lots of different observations. And you can then finally address this question: are the models truly different from one another? Do their distributions overlap, or are they separate, fully separated according to just some simple statistics? And then we have eye candy for ENSO power spectrum. Again, one simulation does not cut it. There's a lot of variability, even if you have, I don't know how many years this is, but it's like 70 years of data. Okay, so I will end here. I give some ideas for how you might apply the package. There's so many things you can, like my own research is very much stimulated by what we get for these packages. I'm happy to talk to you individually. And I'll just leave you with these resources here at NCAR for studying climate variability and change. I've talked about the two bottom ones. The top one is a third one about climate data guide, real observations, and what are the strengths and limitations of different data sets for your particular purpose. Thank you for letting me go on.
Thank you, Clara. All right, we have time for a few questions.
Thanks. I'd really like to ask more about the spectral character of the large ensemble simulations, because many fully coupled simulations, even large ensembles, characteristically have much lower variability at low frequencies than especially reconstructions, but even sometimes observations. And so do you think that this sort of like wider spectral character of the large ensembles is still a function of that sort of null hypothesis that you presented, where we lack sort of the sampling frequency in order to capture the lower frequency variability? Or if not, like how can we explore solutions to the whitening of simulations?
Yeah, great question. I think, you can only look at a power, the power spectrum out to the Nyquist frequency, i.e. half of the length of your data set. So I think, we're just limited, obviously, with instrumental data that we have absolutely no confidence in, variability that I think is largely white or red noise beyond, say, a few multi-decadal variability. And then you have to come in with the paleoclimate records. So I don't know if, I think it's more a function of, I guess we are limited by the data, the observed and paleo data sets that we have to really assess how well models do. I may not be fully getting your question, but I'm happy to talk to you during the lunch hour. Yep.
Before the next question, I just wanted to point out this is the website we've been using all week for the tutorial.
Awesome.
And today we're doing diagnostics, and under additional topics, we have CVDP. And you can see additional documentation within this is in progress, but we've pointed you to the websites and the paper here.
And maybe I'll just make one comment about this. Thank you, Alice. So this is the Climate Variability Diagnostics Package original version that predates large ensembles. So you get much the same information as I showed you, except no information on the ensemble mean and the rank of the observations within the ensemble. So when large ensembles came on board, we decided we needed to make a new version of the package. So there's also CVDP -LE for large ensembles. So maybe we can add that.
We'll update this. You can
Awesome.
see.
So both are useful. But
we were hoping to have more on this, but as we told you, this is new this year, and so
Awesome.
it was just one thing that didn't make it. And then
Cool.
under introduction, we have this community experiments, and there's one of those things is the Climate Data Gateway, and the other one is the Climate Data Guide, which she also recommended. So we just provide a link. This is just what it should look like when you open it. So I just want to point out those are here, and you don't necessarily have to take a picture of the different links, but just trying to make sure that you know there are other ways to get there. All right, next question. We're just going to do a couple more before lunch, so you go ahead.
Yeah. Thanks for your presentation, and I've learned a lot from reading papers by you and your collaborators. I think maybe this is an elementary misunderstanding, but if we are interested in exploring the effect of forcing on climate variability with large ensembles, it seems to me that the large ensembles get the variability with a certain forcing, but then you'd need a multi-model ensemble to get the effect of differential forcing on variability. Or is that not correct? Because if you have just one forcing and one form of variability, it's not clear how the forcing affects the variability over the internal part.
Yeah, but I think, I mean, I personally have written papers on changes in variability. So under evolving, we apply evolving radiative forcing, right? So then you can look at how, especially in this package, you can ask, okay, please show me what the variability looks like for the last 30 years of this century, and then show me what it looks like for the 30 years of the previous century. And that's how you can then compare variability. And there's a new technique which I love called snapshot EOF analysis. I was going to introduce that here, but don't have time. But that's another really great tool. Happy to talk to you about that. So yes, you can get it from, you want to know for a given model, how is the variability affected by the forcing? And you can do that with large ensembles because you have enough sampling. And then you want to know, do models represent that change in variability, force change, differently amongst different models?
Thank you.
Yep.
So I read that for weather forecasting, there's a theoretical limit for how many days out you can forecast. And I'm wondering, because like our stakeholders really want us to reduce the variability in our predictions so they can plan. And is there an analogous like theoretical limit to the reduction in climate variability? And does that question make sense?
It makes a lot of sense, and it's very important to bridge the weather forecasting, world with the climate forecasting world. So the same, for weather, 2 to 3 weeks kind of limit on atmospheric variability. But the ocean brings in memory because it's more slowly varying. And some of that more slowly varying oceanic anomalies, whatever, some of that has some predictability out to maybe a decade. And that is sort of a whole new realm of research that's really blossomed in the last few years, decadal prediction. But that's coming from that the ocean evolves slowly, and so you have some predictability. It's not going to give you 100-year predictability. I don't think it's going to give you much predictability on 30-year timescales. But for certain things like ENSO, we now can predict quite well 1 to 2 years in advance. The Atlantic meridional overturning circulation in the ocean, the conveyor belt, maybe 10 years. But that doesn't control climate, globally, for that whole time period. I mean, the effect of the ocean memory is there, but there's also all this chaotic weather-limited timescale of variability in the atmosphere. So they're both occurring at the same time. But that's the analogy. Yep.
All right, we're going to take one last question here in the back. And Clara said she's around if you wanted to talk to her after and at lunch too.
Yeah, thanks, Clara, for introducing these concepts. And please correct me if I have not understood correctly. So suppose we are doing long simulations with these models, and we want to see the impact of a certain
forcing anomaly. It could be ENSO, it could be NAO, or even sea ice changes. And we need to do multiple ensembles to also sample the variability in a better quantification. But suppose, but there is also a global warming signal in the background. So how could we separate the global warming signal from the forcing that we are trying to study? The impact of the forcing.
Yeah, and I told you there were, in my view, two big challenges. One is the short data records, and the other is we are now in this evolving climate. And how do we remove that, from our modes of variability so that we know we're really looking at the variability itself? And that is very tricky. And if your mode of variability is defined based on temperature, say sea surface temperature, you have a real problem. So for ENSO, you need to, apply some trend or quadratic trend, whatever your fit is, remove that, and then look at the variability about that. With models, you can with large ensembles, you can simply remove the force response at each time step. So you don't have to assume some parametric shape for the trend. In the atmosphere, if it's based on circulation metrics or sea level pressure, at this point, there is not much of, at least according to these climate models, much of a forced mean trend. So I think you don't have to worry too much. But yeah, these are big questions. How do you properly remove the evolving background climate so that you can define these modes of variability? We can discuss more, but it's an open area.
All right, well, let's thank Clara again. Thank you so much. All right, so it's lunchtime. I just have the list again for people who are meeting with a scientist and the room with whomever you're meeting. And these are the people going on the tour. That will meet in the front lobby at noon. So I'd encourage you to go ahead, try to get lunch. And then if you don't know where you're going here, I'll be up at the podium and try to help you get to where you need to go.